Hi, I'm Keiko Hirayama, a Wolfram developer in Scientific Content Group. I'm introducing a new set of data on animal anatomical structures, including canine and equine anatomy 3D models. Hi, I'm Keiko Hirayama, a Wolfram Alpha developer in Scientific Content Group. Today I'm talking about a new set of data on animal anatomical structures, which is available in the Wolfram language. And this is an expansion to existing human anatomy data, which was introduced in Mathematica 10. Yeah, sure. Does this look good? Okay. So this was introduced in Mathematica 10 about 3 years ago, and that includes detailed 3D models like this for over 6,000 anatomical structures. And this offers good learning tools for students or anybody interested in anatomy. And after the release of this anatomy data, we have received several requests about having more other animals in addition to humans. And that was the basic motivation for this project. So now we do have models for additional animals, including dogs and horses. And our overall goal is to facilitate computable access to anatomical knowledge useful for vet medicine or any comparative anatomy analysis. So this is the brief outline of this today's talk. First, I'm introducing the overview of the data structure. And we can access varieties of properties of animal anatomical structures. And we are looking at some key characteristic queries that use those properties. And some notable features of anatomical structures are their hierarchical relations and physical connectivities. And we are looking at networks of those relations. And in addition to textual data, we do have graphics images. And there are some options that have been implemented recently to customize graphical visualization. So I'm briefly going over those new functions. And finally, by applying those tools and functions accessible in the Wolfram language, we can compare the anatomical structures. We are comparing some notable features, both quantitatively and visually, using the tools available in the Wolfram technology. And that brings us the summary of today's talk. And our data is now accessible via the new entity type called animal anatomical structure. And this data set includes comparable information about canine and equine anatomical structures. But some accurations are still in progress, so the data should be expanded further near future. And like existing anatomy data for humans, this data set is based on UMLS, Unified Medical Language System, which is a lexicon type database provided by the US Library of Medicine. So this means that they share the same data structure and same concepts, which make us easy to handle their data. And the UMS data is hierarchically organized, as shown in this simple diagram. For example, dog's pancreas is structural part of trunk, systematic part of endocrine, as well as alimentary systems, as well as member of the structure organs in the dog's body. So we can easily access these hierarchical relation information using the various properties, which I'm going to show you in a minute. And additional information was curated by our intern. We have Hoshi Colina in our group. She's an animal science expert who helped us curate some of our data. And yes. Okay. So I was okay. So for dog anatomy, we have entities for over 1,600 anatomical parts, including bones, muscles, to organs, to body systems. For example, liver, biceps, skeleton, those are known as entities. And we have more than 40 properties to access information about individual structures. And some notable hierarchical relation properties include this constitutional parts property, where you can access the structural part of a particular body part. For example, dog's occipital bone is made of 4 separate parts. And there are additional hierarchical relation properties. For example, system group, you can get the list of organ systems that a particular structure belongs to, or find the complete set of bones in a body, animal's body. So as we curate our data, we noticed that there are not many data sources that have the complete list of all the bones. But we do have information here that the average adult dogs have 319 bones, and actually we can get the names of all the bones. And of course, using our interface functionality, natural language input can be converted to Wolfram language input ready for the evaluation. So here the query was, what are the bones of the dog's left forelimb? And you get actually the list of bones. In this case, left forelimb is the entity and bones is the property. And with this entity property combination, you get the answer. And similarly, we can also ask about muscles of particular body segment. And in addition to these parts queries, we can also ask physical connectivity of the structure, like a bones articulation, or finding a joint for a given bone structure. So now, with all these accessible properties in mind, let's take a look at networks of anatomical structures. So here we use constitutional parts property to get a part of a dog's body. And one of the parts, a hind limb, is made of broken down into even smaller subcomponent structures, including individual muscles and bones. And we can actually visualize these hierarchical relations using a single nest graph function. And in this graph, the center of the graph illustrates the dog body, and these radially expanded groups illustrates the body segments like head, neck, and hind limb, and their subcomponent structures. And in the next example, we use the same function, but including the tissue type, structure type information. So now muscles are colored in red, bone tissues are in blue, organs are in purple. So this kind of tells us that muscle tissues occupied a large part of the dog's body. Quite similarly, we can also build the networks of skeleton connections. Here we use bone articulation property to get information about the bone connectivity of dog's limb. And you make a graph like this to show which bones are connected to which. But of course, it would be nicer if we add bones location information and include that in the graph. And we can estimate the approximate location of the bone using this graphics region centroid property and include that information in the graph. And here we have bone skeleton connection graph with coordinate information included. Oops. And in addition to these textual data, we do have graphics related properties. For canine and equine anatomical structures, we have models for over 800 and 1,000 parts, respectively. For example, this typical morphology property gives you the structural schematic diagram of the structure. And additional image properties include this body location image and this regional location image, where you can actually specify the viewpoint, or you can also get the highlighted version to get the better view of the structure. And this is a small application of the use of the graphics. Here we retrieve the organs of alimentary digestive systems and selectively visualize individual structure like liver, pancreas, stomach, and so on. And not limited to 2D images, we do have 3D graphics models, and our models are scaled based on the average length of femur bones in adult animals, and coordinates are given in millimeter scale. And graphics include meta information about subcomponent structures. So, for example, this is the larynx made of several cartridges, and you can actually add the tooltip with the label for the subcomponent structure and the source information. And it's also noteworthy that we do have capability to do additional geometric computations using mesh regions. And the simple example is finding a surface area using the mesh. Also, there are additional built-in properties to access geometric parameters like mesh volume, enclosing cuboid, region centroid, and so on. And when it comes to customize the graphical visualization, we have Anatomy Plot 3D function. And this function was implemented by Jeff Bryan. Jeff implemented all the graphical related functions for anatomy data. And great thing about this Anatomy Plot 3D is that you can add any structure or any combination of structure, and it's showing this entity listed in here. And by default, there are the tooltips included, so you can actually see the subcomponent structures. And another notable features of this Anatomy Plot 3D are that you can add styles to specific structures or specific tissue types. So, for example, here we specify the colors of particular muscles of the thigh and visualizing in this graphics. And in the next example, we specify the colors of the tissues. In this case, muscles are colored to be blue in dog's limb. And there are also additional options. For example, this plot theme is very handy and nice feature that you can add a scene of your interest to your graphical visualization, like this X-ray and vintage style. And in the following example, we use clip plane options to selectively cut the external layers of the structures to expose internal organs. And in this case, we selectively cut muscle and skin layers to expose internal organs of the dog. And similarly, here we expose the internal structure of the horse, but in this case, we use monochrome style to emphasize the natural color of alimentary organs. So now we do have access to all the tools and functions. Let's take a look at comparative anatomy areas. Comparative anatomy deals with structural and functional similarities and differences across different organisms. And we take a human and a dog as an example to compare their structures. Let's take a look at similarities first. As we might have guessed, our internal organs are pretty similar to dogs. And here we use Anatomy Plot 3D to visualize abdominal organs in classic styles. And here we compare the limb muscles. First we retrieved muscles of the forelimb, and then pass that information to get the homologous human structures. And this is the list. And we can visualize the comparable homologous muscles of humans and dogs here. And that there are a lot of homologous muscles between the two. In contrast, some dogs' neck muscles are quite different from those of humans, and we can get the list of those muscles in a similar manner. And those are unique muscles are featured in this graphic, where those muscles are highlighted in red, and all the other neck structures are in a monochrome style. And we can also quantitatively compare their structures. For example, here we compare the muscle sizes between dogs and humans, and we compare the volume of the muscles normalized by their body mass. And this plot kind of tells us that dogs have some muscles that are larger muscles relative to their body sizes. And we can locate those muscles using this regional location image. And these are the facial muscles and some tail muscles. And it kind of makes sense that dog has larger tail muscles attached to the tailbone, and while tailbones are vestigial structure in humans. And similarly, we compare the size of the bone here, and dogs have some larger distal phalanges, toe bones, and these are the bones. In this table, we simply compare the number of bones, and we can learn here that adult average dog has a total of 42 teeth. This is lower and upper teeth, while humans have 32 teeth, and dogs have 26 ribs, 13 pairs of ribs, while humans have 12 pairs. And the differences in those skeletal structures can be visualized, visually compared. So here we compared a rib cage of human and dog, and 12 pairs of equivalent ribs are highlighted in red, and you can see that dog has extra pair of ribs here. And these are the vertebrae that we use scientific form to color the individual vertebrae. And you can see that dog has long caudal vertebra, tailbone, which is vestigial in humans. And these are the mandibular teeth, lower teeth, where canine teeth are highlighted in purple. And as the name stands, canine teeth in dogs are kind of distinctive structures. And here are ankle bones in vintage style and X-ray style, where the largest calcaneus bone is highlighted in red. So finally, this graphics kind of illustrates the homologous skeletal structures across three organisms: humans, dogs, and horses. And we can see that humans have this collar horizontal clavicle bones, while dogs and horses don't. And humans have this separated radius and ulnar bones, while horses and dogs and horses, those are kind of fused. You can see also the back side here. And the horse has long metacarpal bones, and the phalanges, those are homologous to human middle fingers. And this kind of brings us to the summary of talk. We have a new collection data which is accessible via the entity time in the entity framework in the Wolfram language. And we have several properties to access information like their hierarchical relations and connectivities. And not limited to textual data, we have graphical images and 3D graphics models, and those can be customized for the customized visualization. And the combination of the data sets and the Wolfram technology stack kind of allow us to explore and compare the anatomical structures across various organisms. So what's next? We are kind of expecting to add more information and more models for additional animals. So I'd be curious to know which actually models you would like to see next, and I appreciate any suggestions. So that's all I have. Thank you very much.